Hi, today we are going to look at some more functions of differential equations and just look at their different types of solutions and learn a few new types of separable differential equations that we're going to work on solving. So there's a couple that I want to talk about first. The first one is actually just the simple growth and decay. These are out of order. Simple growth and decay that we've already looked at. That dy dt equals ky, we get that form y equals ce to the kt. Another one that is pretty common, and it will make sense as to why. If we talk about position, velocity, and acceleration, we know acceleration is the derivative of velocity with respect to time, and that form is negative g. And so the solution to that differential equation, the solution to the acceleration differential equation, is negative gt plus c. And if we were to solve this equation as a differential equation, we would solve it as ds dt or dx dt equals negative gt plus c to get the position equation. So that's just really saying that we can relate position, velocity, and acceleration using differential equations. So those two we've dealt with before. Now, the differential equation for exponential growth assumed that the growth continued forever. So when we looked at this growth equation, y equals ce to the kt, we're assuming that it just continues on forever and ever. And we know that there are not many things that will actually just continue to grow without bound. Oftentimes they have what we call a carrying capacity or a limiting factor that caps out where they can grow to. And that type of growth is actually called a logistic growth function. So logistic growth just means that there is some cap to where we're growing. It cannot grow beyond a certain point. There is a carrying capacity or a limiting factor that caps out that growth. Now, the differential equation form looks a little bit messier. It says dp dt, so the rate of change of some population over time, is equal to the constant times this equation p, 1 minus p over L. And the solution that we will get is p equals L over 1 plus a e to the negative kt. Couple things I want you to notice. One, this part right here, this ae to the negative kt, looks decently similar to our exponential growth and decay. Just that part. It is in the denominator at the moment, but we know a negative kt would move that up to the numerator, and we have this L that's new. This L is a constant. This k is a constant as well, and they're going to be positive constants. Now, what I want to do with you first is walk you through the procedure to solve this differential equation. And I've given you some steps that we're going to go through just because it gets a little bit crazy. And so see what you can do to follow along. All right, the first thing I'm going to do is I'm going to separate this equation. So we have the equation dp dt equals kp, capital P, 1 minus p over L. And my goal is to get all my p's on one side and my t's on the other, keeping the baggage with the t's if I can. And so rewriting this, I get this expression, 1 over p times 1 minus p over L dp equals k dt. Ultimately, this is what I want to integrate. Okay, but what I'm going to do first is I need to consider this kind of crazy fraction that's right here and do some work with this. So my goal is to integrate these two sides, and then I want to do work with that fraction before I do this. So I'm going to rewrite this. Notice we're on this step where we're going to use partial fractions to rewrite the left-hand side. If I rewrite this 1 over p times 1 minus p over L, that kind of looks like a plus in there, but that was meant to be 1 minus. I'm going to rewrite this to be, I'm going to find a common denominator first. So I would have 1 over p times L minus P over L. And then when I rewrite this, I'm going to almost copy dot flop. I'm going to rewrite this as L over P times L minus P. Okay, this is where I'm going to use partial fractions. I'm going to let this be A over P plus B over L minus P. Yes, this is a lot of variables that are going on here. And remember, with partial fractions, we would take and multiply everything in this partial fraction right here. So I'm dealing with just this part right here. And I'm going to rewrite that as L equals A times L minus P plus B times P. Maybe we put parentheses around that to help. And remember, then we used the Heaviside method, most of us did. So if we let P be 0, then we get L equals A times L, which means that A has to be 1. And if we let P equal L, then we get L equals B times L, which means that B equals 1. And so I can rewrite this expression as 1 over P plus 1 over L minus P. Okay. Yes, this seems like a lot, but what I'm going to be able to do now is take this expression that we said we want to integrate, and I'm going to rewrite it. So I'm going to take and replace that green portion that we said we were going to rewrite. I'm going to rewrite that as 1 over P plus 1 over L minus P equals, or dP, equals K dt. And now I can actually integrate, because I wouldn't be able to integrate that before. So now I'm going to find the antiderivative of both sides. And we get the natural log of P, or the natural log of the absolute value of P. Let's do absolute value of P, minus the natural log of the absolute value of L minus P equals KT plus C. All right, there is one step with this that's a little bit funky. And I want you to multiply both sides by -1. And so this is where we're going to perform that step. And I'll show you why. Multiplying by -1, we switch the order here. So this would be the positive natural log of L minus P minus the natural log of the absolute value of P equals negative KT minus C. Okay. The reason we would do that step is because then I can rewrite this left-hand side to say the natural log of L minus P over P. And you might say, well, I could have said that in reverse. I could have said the natural log of P over L minus P up here. Yes, you are correct. However, it's this next step that I wouldn't be able to do. Okay, let's continue. This will still be negative KT minus C. And this is the step that will be more advantageous to us coming up. Next thing I'm going to do is I'm going to exponentiate both sides. Again, I could have done that without multiplying by the -1, but I'll come back to it in just a second. That leaves me with, on this left-hand side, the natural log and E will cancel out. So we've got L minus P over P, the absolute value of that, equals E to the negative KT e to the negative c using my log properties. This side, the left-hand side, will be L minus P over P equals, we're going to give it some other name. For whatever reason, this name that they use is A. And A represents plus or minus e to the negative c. So A replaces this and the plus or minus from the absolute value, e to the negative kt. Now my goal is to get L by itself. P by itself. And at the moment, P can't be by itself. So the reason we went ahead and switched that natural log up above is because now I can rewrite this as L over P minus 1 equals A e to the negative KT. And when we do the math here, then we get L over P equals 1 plus A e to the negative KT. Now remember, I want it to be P equals, so P, when I multiply this, let's do it this way, let's take an extra step. 1 over P equals 1 plus A e to the negative KT over L. And if I want what P equals, this will switch to be L over 1 plus A e to the negative KT. And so we just proved that equation actually does work. A bit messier, don't you think, than proving the simple growth and decay. But here's what I want you to see. This solve for y. Well, we don't have a y. I was going through the steps. This should actually say solve for, here this should say solve for p. Okay, a couple things. This parameter L that we have right here, so this parameter L represents our limiting value, our carrying capacity. The parameter K represents the growth rate that we have, the relative growth rate that we have. And then A is like our initial value. So it depends on what happens at that P sub 0 time. Okay, so let's talk a little bit more about logistic functions. And do you have to be able to prove that? No. This is one of those that if you can memorize it, great. If you can't, we need to know the steps, and these steps are a little bit messier. So if I were to commit to memory one of the exponential growth type problems or the logistic growth type problems, this would be it. Okay, so let's keep going. Okay, some important facts about logistic functions that we have. This carrying capacity L is the max, oops, I'm on the highlighter, is the maximum capacity or the maximum population the environment can sustain. So carrying capacities and maximum population and environment can sustain. And as P goes to 0, then the rate of change of the population to time goes to Kp. And as P goes to L, then the rate of change of the population goes to 0. Okay? So the graph of the function P is actually what we call a logistic curve. And in logistic growth, the population grows the fastest when the population is half of the carrying capacity. In other words, the max value of dp dt, the rate of change of the population with respect to time, is equal to P, and it's when P is L over 2. So to find the max rate of change, find the time of the max rate of change is what I want to say. To find the time of the maximum rate of change, all we need to do is we need to take 1 over k times the natural log of a. Okay, so a couple things. This line right here, this blue dotted line in this case, where the graph levels out, this is what we refer to as our carrying capacity. So if we were to look at a slope field, we would see this line where the graphs level off. That happens to be our carrying capacity. Now, what would depend on the slope field and where the carrying capacity is what our initial value is. And we weren't given that necessarily in this graph. Well, we were given that in this graph. It shows that it's going through 0, 1. Now, the max slope here, this max slope, is when the population is half of the carrying capacity. And this max slope is going to be at a special point, our point of inflection. Okay? So the slopes of a logistic growth curve are small at two places, or near two places. They're small as we approach p equals 0, and they're small as we approach p equals L. Those slopes are smallest there. And if we look at this graph, obviously that makes sense. We're small slopes here. The slope gets steeper, 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 and then it starts leveling back out closer to 0. The slopes are steepest at the point of inflection. That's where it will grow the quickest, otherwise known when L equals 2, half of that carrying capacity. Okay. And let's think about what happens if the P is actually greater than the L value. If our population is greater than the L value, then what would happen is our slopes would be negative. Because if our population is greater than that carrying capacity, our population needs to go towards that carrying capacity. So our slopes will be negative, and this would be when the population is decreasing. Okay, so let's look at an example of this. What might this look like on a problem? Okay, so a population of coyotes in a wildlife preserve is modeled by a logistic function. The preserve can support no more than 100 coyotes on the property. Write the differential equation with k equals 0.1, where t is measured in years. Okay, we're going to start this with a differential equation. So it says a population of coyotes is modeled by a logistic function. The preserve can support no more than 100 coyotes on the property. This 100 happens to be our carrying capacity. So we need this information for the L value. So this right here will be our L value. We know our K value is 0.01. And so what we're going to use is the equation, the differential equation that was listed on the front. We're going to use the dp dt equals kp times 1 minus p over L. Okay, so remember our goal is to find the p function. So I'm going to fill in the information with the carrying capacity and with the k value. In this particular example, we were given the information, so my function is going to look like this. dp dt equals 0.1 p times 1 minus p over 100. Great. Now, you could potentially see this equation written just a little bit different. The way we could see this written different is if I were to find a common denominator between this fraction and this fraction. So I would have 100 minus p over 100. And that looks messy. So what I could do is then divide this term by 100. And this would look like this. So it would look like this to start with, 0.1 p, 100 minus p over 100. And then if we multiply this out here, this would give me 0.001 p times 100 minus p. This is the same equation. So just keep in mind, you could see it written a little bit differently, but they say the same thing. Now, the question says the slope field's shown at right. Where does the horizontal asymptote appear to occur? And does it make sense for the problem? Well, our horizontal asymptote appears like it's right here at 100, does it not? And so at y equals 100, does that make sense? Does that fit what we were talking about? Well, yes, because this is the carrying capacity. Now, what would happen if the initial population was above that asymptote? What do you notice? Do you notice that all of these slope field lines are curving down towards it? And remember how we talked about that the slopes would have to be negative if that was the case, and the population would have to be decreasing. So if what we found was the initial population was above that asymptote, that's what we'd be seeing. So we would be seeing the population in decline. So the population will decline. Now, the next part says if the preserve initially begins with 20 coyotes, sketch a graph of P of T on the slope field. So if it begins initially with 20, it'll look something like this. And the way this slope field is going is not very quick, so it might look something like this. Let's make it not curve quite so much down there. Let's make that nice and smooth. Could you tell me, this wasn't asked, but could you tell me where you think approximately the rate of change of this population of coyotes would be the quickest or the highest? Well, the rate of change of the population of coyotes will be the highest when the population is 50. So let's look at 50. And does it make sense that this point right here, we'll call it 12.5 maybe, does it make sense that at 12.5, this population is the quickest? Does this appear to be a point of inflection of this curve? And the answer is yes. So our max value of dp/dt would happen right there. That's our point of inflection. Continuing on with this same example, it asks us to find the general solution. Remember, that's when we don't have an initial condition. So we won't be able to solve for that C. But then it asks us to find the particular solution of the differential equation when P of 0 equals 20. Okay, so I would suggest you write small. We're going to go through this step by step, kind of like on the front in case you don't have the equation memorized. So we wrote that this would be dp/dt equals 0.1 p, 1 minus p over 100. And then remember we separated our variables, or we would separate our variables. So we'd have 1 over p times 100 minus p over 100. And then dp equals 0.1 dt. And my goal is to integrate this. But just like on the front, I am going to do some work here. I'm going to rewrite this side as 100 over p times 100 minus p, which then will be a over p plus b over 100 minus p. So we get 100 equals a times 100 minus p plus b times p. So if we let p be 0, then a would be 1. And if we let p be 100, then b would be 1. So really what I'm doing is I'm integrating 1 over p plus 1 over 100 minus p dp equals the integral of 0.1 dt. Let's come up top. So we get the natural log of the absolute value of p minus the natural log of 100, or the absolute value of 100 minus p, equals 0.1 t plus c. And remember, this is where we are going to multiply by the -1. So it rewrites the order. Oops, that was absolute value of the left-hand side. And this will be -0.1 t minus c. And if we work to combine this, we're going to get the natural log, or we're going to get 100 minus p over p. Those would be absolute value. The natural log of that equals -0.1 t plus minus rather c. And I'm going to exponentiate it. And I'm going to take a shortcut here because I know that would give me 100 minus p over P equals A e to the negative 0.1 t. And if I were to solve for P at this moment without using the initial condition, to be honest, this is probably where I'd use the initial condition. But if I were to solve this using the initial condition, I would get 100 over P minus 1 equals A e to the negative 0.1 t. And moving the 1 over, doing some math, we get P equals 100 over 1 plus A e to the negative 0.1 t. Could we have remembered the formula from before? Absolutely. So if you know that formula and you take a second to look back at that original formula and remember the original formula said P equals L, that's our carrying capacity, 1 plus A e to the negative K T, and we were given K and we knew L. Could we get there without doing all of these steps? Absolutely. Feel free to skip those steps. They are not required. It is okay to go right here. Now, I told you we have an initial condition. And with this initial condition, I probably would have plugged that in this step here before going on. It doesn't really matter where you plug it in, but I just think right here would be pretty easy to plug it in. So if I plug in my initial condition here, we know T is 0 and the result is 20, or a population is 20. So we would have 100 minus 20 over 20 equals A e to the negative 0.1 times 0. And so we get A e to the 0, which means A equals 100 minus 20 is 80, divided by 20 is 4, so A would be 4. So the actual equation, this is what we call our general solution. And our particular solution would be P equals 100, 1 plus 4, e to the negative 0.1 t. This one is called our particular. This is the one that if the initial population is 20, this will allow me to solve any other problem along with that particular, that initial value. So the next question says, when will the coyote population reach 80? Now it's plug and chug. When will the population reach 80 means 80 is P. And we're trying to solve for T. Now, order of operations is what will usually get us a little bit messy on this one. So think of this way. We would be cross multiplying. That's over 1. When I'm cross multiplying, however, I want to then get this T by itself. So do you feel comfortable sitting with this step? Good? Okay. Now I'm going to work to solve this, and we're going to use a calculator. Most of the time this will be a calculator question. So hit pause and go ahead and finish solving this one. And then see if you can answer G and H, and we'll come back to those in just a second. All right, if we go through the calculations of this, it depends on how much you want to, how much math you want to do in this. It doesn't really matter. We could do this simply. We could do it a little bit more complex. I'm going to go ahead and subtract 1 from 100 over 80, which would really, I could reduce as well, but subtract 1 from that. So I really get 20 over 80. 20 over 80 would be 1/4. So I have 4 e to the negative 0.1 t equals 1/4. I'm going to divide by 4, so I get e to the negative 0.1 t equals 1/16. Taking the natural log of both sides, we would get the natural log of 1/16 equals negative 0.1 t. So t is going to be the natural log of 1/16 divided by negative 0.1, which according to my calculator gives me 27.726 years. That's years when the coyote population will reach 80. All right, so when is the coyote population growing the fastest? Well, we said that the population grows the fastest if we take the carrying capacity and divide it by 2, so at 50. And then we said that time is going to be when we have 1 divided by that constant, that k, times the natural log of 4. And when we do this math, we get t is approximately 13.862. Okay, and what about this last question? Find the limit as t approaches infinity of this function p of t. What'd you get? This should be easy because it's the carrying capacity. The limit as we go towards infinity, it can never be more than that carrying capacity. So that L value that we have would be the limit as t approaches infinity of this function. So it's 100. Okay, so that's an example of what we call logistic growth. So that's another type of differential equation that might come up. But if I were to pick one type of differential equation that we see the most, it would probably be this Newton's law of heating and cooling. So let's focus on Newton's law of heating and cooling now. So Newton's law of heating and cooling, apparently here it just says cooling, states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and some fixed constant B, usually the temperature of the room or the temperature of whatever it's in. So it says that the rate of change in the temperature of an object is proportional. Here's the rate of change of an object is proportional to the difference between the object's temperature and some fixed constant B. So if K is greater than 0, we have growth. If K is less than 0, we have decay. And we get this solution here. So P equals AE to the KT plus B, where A is the initial value minus B and Y sub naught is what we call the initial temperature or whatever. One of the keys that you're going to want to take away from this before we get too far into it is to remember to factor out K before you start solving the differential equation. Otherwise, it gets really messy. So different types of applications that use this differential equation, Newton's law of heating and cooling, falling objects approaching terminal velocity can use this, and pressure inside a deflating container that is approaching the outside pressure can also use this type of application. What we're going to do is look at the most common one, which would be Newton's law of heating and cooling. Okay, so here we go. So you bought your favorite frozen coffee drink on the way to school via the drive-thru. Your car is always kept at a constant 65 degrees Fahrenheit. Traffic, unsurprisingly, was terrible, and you spent 10 minutes getting to school. To me, 10 minutes sounds like you're doing pretty good. The drink warmed to 35 degrees Fahrenheit because you checked it with your temperature probe at the red light. Then, 2 students had a rear-end collision, sounds about right, and another 10 minutes passed trying to get into the school parking lot. Parking lot, not log. You check your drink again, and it warmed to 50 degrees by the time you got into the parking lot. Let's use Newton's law of cooling to estimate several things. 1, what was the frozen drink's original temperature? So, I'm going to start and show you from the very beginning, and then show you where you can skip to if you remember your equations. Again, it all depends on how much memory space you've got. So, Newton's law of heating and cooling says that our temperature, dy dt, is going to be proportional to K times y minus, and this is the value that is held constant. So this is going to be y minus 65. So this 65 right here is going to be what goes in this parenthesis right here. Now, I'm going to separate these as much as possible. So separating this, we get 1 over y minus 65 equals k dt. Oops, I lost my dy. And I'm going to integrate both sides. And so far, this doesn't seem out of the ordinary at all. Seems pretty straightforward. And so we would get the natural log of the absolute value of y minus 65 equals kt plus some constant of integration. And you guessed it, we're going to exponentiate now. So this will be e raised to the natural log, e raised to this kt plus e. And skipping maybe a few steps, we would get y minus 65 equals some constant times e raised to the kt. Now, solving this, we get a equals, oh no I don't, what am I writing? What am I saying? We get y equals a e to the kt plus 65. Now, you can skip to that point. If you know that equation and you feel good with that, skip to it. Now what we're going to do is we're going to try to solve for the variables. Clearly right now I have too many variables. I have a, I have a k, I need to deal with something. Okay, so let's go back into the problem and let's define some ordered pairs that were given to us. And so let's start here. You spent 10 minutes getting to school, the drink warmed to 35. So that particular ordered pair would be y of 10 equals 35. Then we have another ordered pair. It says 2 students had a rear end collision, 10 minutes more passed, and it warmed to 50 degrees. So then it would be y of 20 equals 50. Now, my goal is to find the frozen coffee's original temperature. So what I'm really trying to find here is y of 0, and I don't know what that will be. So let's go through the process. I have 2 ordered pairs, so I'm going to plug them into my equation. 35 equals ae to the k times 10 plus 65 for the first one. And then my second one would be 50 equals ae to the k times 20 plus 65. What you'll notice here is I don't actually have enough information to solve for them, except that I have 2 equations, which means I have a system. So let's go through and combine these equations. If I take and subtract on the green equation the 65, that leaves us with negative 30 equals ae to the k10. I'm just going to write 10k. And if I, in the purple equation, subtract the 65, we're left with negative 15 equals ae to the 20k. All right, so doing some math there, I am going to divide these 2 equations. The reason I'm going to divide these 2 equations is because my goal is to figure out one of my variables, either a or k. But if I divide these equations, it leaves me with 2 equals e to the negative 10k. Thus, I only have one variable to solve for here. So I'm going to take the natural log of both sides. So we get natural log of 2 equals negative 10k. So then k equals the natural log of 2 over negative 10. Okay, what I'm going to do now is I'm going to pick one of my equations. It doesn't matter which equation we pick that we started with. So I'm going to take this equation, and what I'm going to do with it is I'm going to plug in my k value. So we have negative 30 equals ae to the 10k. And in k, I'm going to replace with natural log of 2 over negative 10. What that gives me is negative 30 equals ae to the 10's cancel out, leaving me with negative natural log of 2. Or if we use our log properties, we get negative 30 ae to the natural log of 1/2. The beauty of that is we have e to the natural log, which means we get negative 30 a times 1/2, which means a equals negative 60. So I have enough information to write my model now. Y equals negative 60 e to the natural log of 2 over 10 t plus 65. Now, this didn't answer my actual question, but I can figure it out really easy from here. Is what was the frozen coffee's original temperature? And remember, we said that that A value is the difference from the initial value and the surrounding room. So if I take and combine these two, or I substitute in y t equals 0 to solve for y, we would get y equals negative 60, sorry, I need to scroll, y equals negative 60 e to the 0 power plus 65. Otherwise, y equals 5 degrees. So my coffee's original temperature was 5 degrees Fahrenheit, was the original temperature. All right, see if you can hit pause and try the next two examples now that we set this up using our differential equations. So just another fun example of differential equations. So hit pause and try the next few. Hopefully what you realized is we're going to be going back to this model. Yes, we use this model to get the initial temperature, but this model is still key, paramount to everything we do in this next example. When would the drink reach a temperature of 63? So 63 equals negative 60 e to the negative natural log of 2 over 10 t plus 65. I just need to solve this now. So to solve this, I'm going to start solving by subtracting. So we get negative 2 equals negative 60 e to the negative natural log of 2 over 10t. Divide by negative 60, we get positive 1/30 equals e raised to the negative natural log of 2 over 10 t. If I exponentiate, rather take the log of both sides, we'd get natural log of 1/30 equals the negative natural log of 2 over 10 t. So solving this, we get t equals negative 10 natural log of 2 over natural log of 2, natural log of 1/30. And I just type that in my calculator and go. So we get t is approximately 49.069 minutes. So I can expect a drink that started at 5 degrees. Remember, it started at 5 degrees up here. At a constant car temperature of 65, assuming that never fluctuates, my drink would reach a temperature of 63 degrees Fahrenheit in 49.069 minutes. Now, could this drink ever go above 65? No. This is an example of a logistic growth as well. If we're in a constant temperature of 65 and that doesn't change, we cannot expect my drink to get hotter than 65. It won't. It cannot, unless some outside heat source is acting on it. All right, what would the drink be after an hour? Well, this is also just a plug in. So y equals, back to that original equation, negative 60e to the negative natural log of 2 over 10 t plus 65. I'm going to go ahead and replace this t with minutes. Now keep in mind we're using minutes, so this would be 60 in minutes. And then this is just a plug in. So I'm just going to type this in my calculator and I get 64.063 degrees, and that's Fahrenheit. And again, there we are. After an hour, I'm still not up to 65, but I definitely won't pass it. So these are all examples of types of differential equations. And it's really up to you to commit to memory which equations you think are harder to solve for, or if you want to just remember how to solve these differential equations, that works too. So now your job is to try the logistic growth worksheet. Have a good day.